Okay, we're going to do some more momentum review. So again, we're doing conservation of momentum, and in this case, we have a classic physics problem where a bullet, it has a velocity, it becomes embedded in a block, and then they're going to move off together with the same, together as a combined mass, but in this case, we're going to have friction. So it says a 5-gram bullet, so I'm going to call that MA. And one of the things I want to do right away is I want to convert the grams to kilograms because I'll forget. So it's 0.005 kilograms. Is fired horizontally into a 2.5 kilogram wooden block, so that's MB, resting on a horizontal surface. The coefficient of kinetic friction, so we'll say mu sub K, is equal to 0.2 between the block and the surface. The bullet remains embedded, so this is my before. This is my after. So now the bullet is inside the block, and which is observed to slide 0.250 meters. So that's how far it's going to go D before stopping. So before stopping, I also know that that means that what? The final velocity is 0. Again, these are called hidden variables. I have to read a problem, and there's certain words that mean something. What is the initial speed of the bullet? So I want to find the initial speed, V naught. All right. Because we're dealing with forces and friction, the first thing I need to do is I need to draw my free body diagram. So here's my block. This is my surface. Again, I have to establish my sign convention. So I'm going to use my standard Cartesian sign convention and say up and to the right is positive, which means the block is going to be moving to the right. Well, if the block is moving to the right, that means that friction is going in the direction opposite the direction of motion. My weight is going to act down, and my normal force is perpendicular to the surfaces in contact, which is just goes straight up. So that makes it kind of easy. So what am I going to do? So first of all, I know the frictional force is equal to mu times F of n. Okay? And you might say, why did you do that first? Well, first, I know this is a momentum problem. So in order to solve this problem at the end, what you would do is you would think of conservation of momentum. So my conservation of momentum says the total momentum before is equal to the total momentum after, and I want to find the velocity of this little bullet here. So I know that MAVA plus MBVB, they're going to be combined. Remember, the equal sign is the collision, the event. MA plus MB times V prime. So if I rearrange the equation, and don't forget that this is 0, because the velocity B is 0, and I want to solve for VA, I would get VA is equal to, and I'm just going to divide by that, MA plus MB V prime divided by MA, because that term is 0. The problem is, and this is how, when you don't know what to do, you go to the end. So here's my conservation of momentum. I have this, I have this, I have this. I do not know what this is. So in order to find this velocity, I'm going to have to do some other physics. And I see that they give me all that other stuff. So if I knew V prime here, okay, and it goes a certain distance, I know here I'm going to end up, I could find the kinetic energy here, and then here the kinetic energy is 0. I also know that work is equal to the change in energy. So then what I would do is I would end up saying work is equal to the frictional force times how far it goes. But before I do that, I have to find the frictional force. So that kind of tells me the steps to do. All right. So number 1, the frictional force is mu times F of n, which is mu mg. How do I know? Well, the normal force is equal and opposite to the weight. All right. So that's going to be 0.2 times 2.505. I'm going to add these two together. Kilograms times 9.8 meters per second squared. So when I do all that, the frictional force comes out to be 4.91 newtons. So that's step one. And we're going to come back to this later, once I find V prime. All right. Step number 2. So I know F of F. So now I want to find the work done by friction, and then I'll end up doing the work is equal to the change in energy. So 2 work is equal to FD. So it's equal to F of F times D. So 4.91 newtons times 0.250 meters. And I'm going to write negative because when I look at my free body diagram, the frictional force is going opposite the direction of motion, so that's going to be negative. Then I know work is equal to the change in energy. So that's negative 1.23. So the final kinetic energy is 1.23. And I know that kinetic energy is equal to 1/2 mv prime squared. So in this case, the final kinetic energy is 1/2 the mass. In this case, they're embedded, ma plus mb times v prime squared. And this is how I am going to find v prime. So I'm going to rearrange the equation, and I want to solve for v prime. It's very tempting just to plug your numbers in, but that's how you make a mistake. So we're going to rearrange our equation. Since we're solving for v prime, I'm going to leave it on this side of the equal sign. So what I'm going to do is I will multiply both sides by 2. So I'll have 2kf is equal to ma plus mb times v prime squared. I'm going to divide, so I'm going to have 2kf over ma plus mb is equal to v prime squared, and then I'll take the square root of both sides. So now I have radical 2kf over ma plus mb is equal to v prime. Now when I substitute in my values, I won't make a mistake, because the most common mistake is to forget that square root. So you have 2 times 1.23 joules divided by my total mass, which I know is 2.505 kilograms. And when I do that, V prime comes out to be 0.991 meters per second. So once I have my V prime, I take this and I put it back in here. So I have VA is equal to MA plus MB times V prime over MA. So it's going to be 2.505 kilograms times 0.991 meters per second divided by the mass of the bullet, which is 0.005 kilograms. Don't forget to convert. And remember, when you carry your units and cancel them, it's a foolproof way to check your work in physics. So you check, so you never have an algebra mistake. So VA comes out to be 496.5 meters per second. And then we think about this. And we use our knowledge of everyday life and say, wow, that's really fast. Well, it's a bullet. And bullets go fast. So again, when you don't know what to do, you go to the end and you let the problem solve itself. Because you go to the end and say, okay, I used my conservation of momentum, but I wanted to find the velocity of the bullet before, but I needed the combined velocity in order to do that. So then I look at what else I have to help me.